Okay, now we're recording. So here you're asked to sketch the graph of f prime given the graph of f. Now, if you're given the graph of f, as you have here, and you can see that f is a piecewise function where each piece is linear in nature. So what you need to do is recognize that the slope of the graph of f for a particular x interval will be the y values of the graph of f prime for the same interval. So let's look at this portion right here. What x interval goes with that? Right here. What's the slope of that portion? -2. Those will be the y values, or that will be the y value for that same interval on the derivative graph. So -2 is the slope here. It's pretty obvious, down 4, right 2. So you're going to graph y equals -2 on the derivative graph for that same interval from -3 to -4. Then we look at the next interval from -4 to -2. What is that slope? Up 2 over 2. So that slope is 1. That's going to be the y value on the derivative graph for that same interval from -4 to -2. Now, why am I putting open circles at -4 and -2? Because they're open intervals on the table here. Also, not the fact, I shouldn't say because you guys don't know this yet, but also what is good for you guys to know is that corners, the derivative does not exist. And that's because the left-hand derivative does not equal the right-hand derivative. We did have a discussion of that in the video, which I'll go over again in about a few minutes from now. The left-hand derivative is the slope of the tangent lines to the left of the point that you're looking at, and the right-hand derivative is the slope of the tangent line to the right of the point you're looking at. So if you're looking at the point where x equals -4, we see that to the left of -4, we have a slope of -2. To the right of -4, we have a slope of +1. So it's almost like -4 is kind of conflicted. It's like I see a slope of -2 on one side, I see a slope of 1 on the other side. So I don't know what my derivative is. So we say it does not exist. That's another reason why we put a circle there. And then of course, if you just keep going through all the other intervals and you get those, whatever slopes you get from the original graph will be the y values on the derivative graph. Let's look at another one. If I move on to this one. Now, this is a curve, right? I mean, it's definitely not linear in nature. And these are estimates, right? So like I could draw a lot of different tangent lines if I so desire. Like I could draw a tangent line here, or here, or here, or here. A lot of different tangent lines I could draw. And I want to estimate their slopes. Like for at point A, sometimes it helps if you use like a ruler, like kind of like, you know, if you were to get a ruler out or a straight edge and just drew a line and then kind of account it. Okay, I go up 4 units over 1 unit, so slope is 4. So it's not terribly accurate, but still the same concept or methodology. What you want to do is find the is that whatever slope you get for all the tangent lines for A, B, C, D, E, F, G, those slopes are going to be the y coordinates on the f prime graph. So the f prime graph is down below. So for example, at x equals -4, slope of the tangent line for the original graph was 4. So we're going to do plot -4, 4 on the derivative graph. And you do likewise for all the other points. Now what you're going to notice is that as the graph is rising, so right now the graph is rising until it hits its peak, all the slopes are positive, all the slopes of tangent lines. So naturally, all the y values on the derivative graph will be positive as well. So this portion of the derivative graph is entirely above the x-axis because on the original graph, the y values are increasing. When the y values start to decrease, let me change colors. When the y values start to decrease, now our tangent lines are negative. So the y values on the derivative graph are negative. So remember, slope of f graph equals y coordinate of f prime graph. That's essentially what we're doing. And so we start seeing that when the graph is dropping in y values, the derivatives are negative. So we put negative y values on the derivative graph. And then naturally we're increasing again. So now the derivative graph's above the x-axis. And that's what's summarized in the bullet points down below. You see that summary right here. Like what can you say with the y values of the graph of f prime, blah, blah, blah. When f is increasing, f prime is positive. When f is decreasing, f prime is negative. Or what about when the derivative graph crosses the x-axis? So that means that, or let me take it back. On the original graph, you have a horizontal tangent. So in that case, then the derivative is going to be 0. Here we see it's in action again. So now you actually have to just do a little matching. Like, which one has a slope of -3? Well, we see that there are 2 points that have a negative slope. At C and F. So we go with F for -3. So C is not going to be as steep, we'll say -1. Horizontal tangent at E, boom, there you go. 1/2 at A, 1 at B, and then D is way more steep. Okay. What's going on here? Well, yeah, one-side derivatives. We're gonna spend some time on that today. It's gonna be a little abstract, so just buckle up because it's gonna be a little bumpy. But I'll help you guys with it, and it's gonna take some time to absorb this stuff. So just be patient, trust the process. But really, if you think about it, it's not that much different than left and right hand limits. Here you have h approaching 0 from the right side. Here you have h approaching 0 from the left side. So when h is approaching 0 from the right side, h is positive, just small. Here, h is negative. But small also. And so we're going to talk about that a lot today, one-side derivatives. For here, you have another piecewise function, and you have these endpoints. At endpoints, we still say the derivative exists. You just use the appropriate one-side limit. Like, obviously, this is a left endpoint, so there's nothing to the left of it. So naturally, use the right-hand derivative. Here, you have a right endpoint. You have nothing to the right of it, so naturally, use a left-hand derivative for that one. So use the appropriate one-side derivative, and then you just kind of just put the endpoints there on the derivative graph. And then here, in example 8, you have another piecewise function, and you're asked to prove that there's no derivative of x equals 1. So what you do is you find the left-hand derivative, just using this formula up above. And when you have 1 plus h, remember h is negative. So 1 plus h is actually less than 1. It's like maybe 0.999. So you're going to be using 2x squared for that. That's why you use 2x squared there. You worked it all out. And we got 4 as our left-hand derivative when we did that limit. For the right-hand derivative, you do when h is approaching 0 from the right side. So h is a little bit positive. So when we have 1 plus h, it's like 1 plus a small positive number, it's like 1.001. So now you're using 5x minus 3 here. You work that out, and you get that limit being 5. So obviously, these two values are not the same. And what's happening is if I were to draw a tangent line ever so close to 1 on the left side, it's going to be a slope of 4, as we expect. Whereas the other one's going to be a slope of 5, if I do a different color there, because that's just a horizontal line. So it's almost like the blue and green lines, they kind of look the same because the slopes are pretty close, but are not, right? Because 4 is not equal to 5. So you have a corner, believe it or not. There is a corner at x equals 1. It's just really hard to see because the slopes are so close together. But because the left and right-hand derivatives are not identical, then we can't say it's differential at x equals 1. So there's no derivative at x equals 1. And that's the reason why you don't have derivatives at corners, because the left-hand derivative is not equal to the right-hand derivative. And that's the definition of differentiability, just like the definition of having a limit exist. You need the left-hand derivative equal to the right-hand derivative. If they don't, derivative does not exist. And we're going to talk about that again a lot in 3.2. Question, is 1 plus h the only part that changes? Yes, that is right. The 1 plus h does change because h was positive over here, but negative over there. So 1 plus h, think of 1 plus h is like 0.99 when that's happening. Think of 1 plus h as like 1.01 when that's happening. And because the piecewise function takes on different values when x is less than 1 or greater than 1. So you have to use different functions for that. Whereas f of 1, you're always using 5x minus 3 because that includes 1. So that's what's happening there. And then finally, for sketching graphs, here has a sketch graph f that has the following properties. I made a little mistake there. I had the corner at 0, 0. That was wrong. Yes, there's a point at 0, 0. Absolutely. And this part is a little weird. So here's how you have to look at this. The slope for each interval sorry, that was incorrect. I was saying, if I'm taking the slope of a derivative graph, that's actually gonna be a second derivative. We'll do that. We are gonna do second derivatives, it's just we're not ready for that yet. Sorry. I meant to say this. The y value for each interval in f prime graph equals the slope for each interval in the f graph. So we were asked to make the f graph. So the y value here is -1. So slope here is -1. So it's reversed. Before, when you get the original graph, you had the slope and you convert that to the y value on the derivative graph. Now you take the derivative of the y value. So you take the y value of the derivative graph, and that becomes a slope on the original graph. And this slope here is, sorry, this y value here is 2. I know you can really get confused. This y value here is 2, so that's gonna be the slope over here. Now, what's happening is that when this interval is from -infinity to 1, this interval is from 1 to infinity. So naturally, I'm gonna draw a slope of -1 from -infinity to 1. And I'm gonna pass through 0, 0, because 0 is included in that interval. That's kind of the strategy. 0 is included in that interval. And when does the interval stop? When does it change? All of a sudden, we have a change of slope, or the derivative changes at x equals 1. So now you gotta do a new slope at x equals 1 because we see that from the derivative graph. And so then you draw over there. So that's why there's a point at 1, -1, because we pass through 0, 0, and we pass through 0, 0, we have a slope of -1, and we keep using that slope until we hit x equals 1. So it happens we stop at 1, -1, and then we go to a different slope. So that's how that one's done. And of course, it's continuous. You assume the continuity bed. So that's what's happening there. So hopefully we're okay with that. And then look in the Google form. I'll stop this recording. Google form is right here. So what do the y values in the graph of f prime represent in relation to the graph of f? The y values f prime graph are the slopes of the tangent lines on the original graph. So slope of the tangent lines, right? So good, you guys are getting that. Describe the process generating a graph of f prime when given the, so if you're given the graph of f, take the slope of the tangent lines, and those become the y values on the f prime graph. So the x values of the f prime graph are the same as x values in the original graph, yes. Use the same intervals or whatever. But the y value on the f prime graph is now the slope of the tangent lines on the original graph. So that's good. That's correct. Yes. This one actually was kind of weird because you have x cubed, which I know looks like this. No, looks like this, kind of. There's a horizontal tangent actually at x equals 0. And when we did derivative of this, if you have y equals x cubed, we did do derivative of this the other day. It's 3x squared. So that derivative is not below the x-axis, obviously. So that's obviously out. So I'm glad no one picked anything in red. Now, does the graph, it does, the derivative graph does cross the x-axis. It crosses over here once. Actually, it bounces off of it. It is technically above the x-axis too, but I didn't make this as a select more than one choice option. I just said you had to select one choice. So it's kind of weird. So if you said either the blue or orange, that's fine. I actually just edited this and changed and got rid of that last choice. But just know it's not below the x-axis, right? It's above the x-axis, and it does touch it once for the derivative graph. And if 4 was, you select more than one choice. All of them are true except for a vertical tangent line. You can't have a vertical tangent line if the derivative graph crosses the x. So if your derivative graph crosses the x-axis, what does it represent the original function? So remember, when you have, let me actually go back to the notes. That's probably better. I'll go back to the notes. So here's a derivative graph, right? That clear across the x-axis. What did that represent? At negative 1.7, I guess, that represents a high point. We had a high point at C. At 2, that represents a low point. We had a low point at E. So it could represent higher low points. It doesn't have to. You know, when you cross the x-axis, it depends on how the derivative graph's crossing the x-axis. And we'll talk about that, I think, in the 3rd or 4th unit in this class. But it could represent that, you know. Also, it could represent horizontal tangents, right? Also, you have a place on the graph where sometimes graphs will flatten out. They kind of like this like flat portion, and they keep increasing. So it's neither a high or low point, but it's a place where there is a horizontal tangent. So those are all things that could represent. Now, if you have a vertical tangent, we're going to talk about that on Monday next week. If you have a vertical tangent for a curve, your slope is actually undefined. So it's not going to show up as an x-intercept on the derivative graph. Actually, it'll show up as nothing, or like a hole or something like that. But we're going to explore that in 3.2. So all of them are true except for the vertical tangent bit on the Google form. There's a question in the chat. Does the derivative equation have to be fully differentiable for a function or just fully differentiable for an interval? Yeah, I think it's the second part, Lizzie. So it has to be differentiable for whatever interval we can find the derivative on the original graph. So we're actually going to talk about that later today in 3.2. So you may have like a function that could be continuous, but there might be only certain parts of it where you can't take the derivative. And so in that case, it's differentiable there. We're going to actually have that discussion very shortly. But good question. Yeah, and then going back to the Google form, and then, yeah, I made a mistake there. I just thought the corner was at 0, 0 for the last example of 3.1 notes. I was a little careless there. That was my fault. But good, you guys are paying attention. And I'll be honest, I'm not deliberately making mistakes. I actually am making these honest mistakes. I wish I could say I did them deliberately to keep you guys sharp, but it's good that I catch myself quickly and that you guys are noticing it. So that's good. Okay, so now let's get the 3.2 notes. So I'm going to spend maybe about 30 minutes on the 3.2 notes. And then the last 15 minutes of class, I'll go over any questions you have from homework. I know someone, and Avita, I know you asked about 42 C and D. We'll get to that, don't worry. But let me start the notes first, and then we'll get to your question about homework. So I'm going to stop the recording.